The first talk of today is by Meusburger from Friedrich-Alexander-Universität in Erlangen-Nürnberg in Germany, and the title is Three-Dimensional Dijkgraaf-Witten TQFTs with Defects. The floor is yours.
Thank you for the very nice introduction, and I want to start with a thank you for the organizers and for the Newton Institute that make this workshop possible. I'm going to talk about three-dimensional Dijkgraaf-Witten TQFT with defects, and my talk is one of the more mathematical side. So yesterday there were many more physics-oriented talks. Mine is mathematics-oriented, but I hope to convince you that it's relevant to physics. And I would also say, if you have questions in between or you want me to explain something in between the talk, then just ask. Okay. So what is this about, and what did we want to do, and what is the relation of this with the physics of defects? Okay, so this is in the framework of TQFT, an ordinary TQFT, and here I'm only talking about three-dimensional TQFTs. So a three-dimensional TQFT is a symmetric monoidal functor from three-dimensional cobordism category to the category of vector spaces. What does this mean? Well, the cobordism category here, it has as objects closed two-dimensional surfaces, and as morphisms, certain equivalence classes of three manifolds with boundary that connect these two surfaces. So you can see them as boundary components. And such a symmetric monoidal functor defines three manifold invariants. The three manifold invariants you get by simply taking a cobordism that is a three-manifold without boundary, so a closed three-manifold, and you see it as a cobordism from the empty two-manifold to the empty two-manifold, and then you get a complex number, like a linear map from the vector space C to itself, and that's a three-manifold invariant. So that's what an ordinary TQFT is. Now the question, what is a defect TQFT? A defect TQFT is something similar, but now this three-dimensional cobordism category is equipped with defects. So I'll explain this in detail later on. But what it essentially means is it has a stratification, so there are distinguished submanifolds of various dimensions in it, namely the domain walls, the line defects, the point defects, and so on. And what we have is now a symmetric monoidal functor of this stratified cobordisms and stratified surfaces into the category of vector spaces. And of course, you can again consider the case where you just have a three-manifold without boundary. You will get a number, but this is no longer just the invariant of manifolds, but it has something to do with the stratification as well. So where in the manifolds are the defects? Okay, so that's the mathematical picture. And so why is this relevant to the workshop? Well, it has applications in condensed matter physics, topological quantum computing, and also in conformal field theory, but the latter requires more work. And in particular, one can use this to describe defects in quantum double model and Levin-Venn models. So roughly speaking, if I just consider this three-dimensional TQFT, the ground state of a quantum double model on a surface or Levin-Venn model would be the vector space that this TQFT assigns to the surface. So you can see these models as the two-dimensional part of a 3D TQFT. But the mathematical formalism is of course different. But essentially, quantum double models are the two-dimensional part of what I'm considering. And if one considers quantum double model with defects, this would be the two-dimensional part of this here. Okay. So what was the aim of this work? So we wanted to give a kind of more geometrical and gauge theoretical description of this picture. So state sum models with defects and also condensed matter physics models with defects are known. And mostly they're based on choices like triangulations or certain cell decompositions. And they're very concrete, and then often they also use diagrammatic calculus for higher categories. And we wanted to give something that is closer to gauge theory, or a more geometrical way of seeing this, and does not involve choices of triangulations or of cell decompositions or of skeleton or anything, and no diagrammatic calculi, and that should also be in the end rather simple and computable so that one can do examples. Okay. So before I explain the defects, I'll explain a little bit about three-dimensional Dijkgraaf-Witten TQFT without defects. So essentially, this is a machine. As an input, you take a finite group. Any finite group, it need not be abelian. And what you get is such a symmetric monoidal functor from the three-dimensional cobordism category to the category of vector spaces. So here I've kind of schematically drawn a cobordism. So you have here some two-dimensional manifold sigma 0. Here you have a two-dimensional manifold sigma 1. And in between, you have the three-manifold X that has as a boundary. The boundaries is diffeomorphic, disjoint union of this and of this. And I'll denote this with this notation, and the bar just means an orientation reversal. So all the manifolds here are oriented. So we have a cobordism here, and the TQFT assigns to this cobordism a linear map that depends on the three-manifold X that goes from the vector space for the surface here to the vector space of the surface here. And that it's symmetric monoidal just means that the tensor product here, which is the disjoint union of the manifold, so you just put them together without any interaction, is mapped to the tensor product here. Okay, so how does this work? What does it look like concretely? Well, before I say what it looks like concretely, I want to mention, so if we have no boundary here, then to the empty manifold sigma 0 or sigma 1, we have the vector space C. And then this is a linear map from C to C, so it gives you a three-manifold invariant. Okay, so how does this look like concretely? You can either describe it in a fairly abstract way or in a concrete way. So the vector space that we associate to the surfaces here is a free vector space generated by a certain set. And this set you can see as isomorphism classes of functors from the fundamental groupoid of the surface. So fundamental groupoid is like fundamental group, but we have infinitely many objects, namely all the points of the topological space, and then homotopy classes of paths. So every surface here has a fundamental groupoid, and here we consider the functors from this fundamental groupoid into the group viewed as a groupoid with a single object. So you have just one object, and the morphisms in this groupoid are then the group elements. And then you consider isomorphism classes of that, and you take the free vector spaces generated by them. If the surface here is connected, you can write this in a much simpler way. You can say you just consider the group homomorphisms of the fundamental group of the surface with respect to a certain base point into the group G up to conjugation. And then you take the free vector space generated by this. And this is a finite dimensional vector space. And then the linear map that is associated to this three-manifold here, you can give it in terms of matrix elements. So here A0 and A1 are certain isomorphism classes of functors here. And you can express this matrix element as just the cardinality of the set of functors from the fundamental groupoid of the three-manifold into this groupoid here that is restrict appropriately at the boundary. So at the boundary they must give you this and this, and they're considered up to certain natural isomorphisms, and these natural isomorphisms here need to be trivial at the boundary. And in this way you can really write down this linear map. So this is how it works without defects, and this is very old. This goes back to Dijkgraaf and Witten and Fried, Quinn. Okay, and this is what the TQFT without a defect looks like. Now, yes, and here you can also see if it's connected and the boundary is trivial, then you will just get a number, and this number is the number of group homomorphisms from the fundamental group of the 3 manifold into the group G up to conjugation. So for the 3 manifold, it's the number of group homomorphisms. For the 2 manifolds, it's the vector space generated by such group homomorphisms. Okay. Now the aim is to put defects into this description. Defects are essentially lower dimensional submanifolds, and they should be decorated with higher categorical data. Roughly in the way that Lukas has described yesterday. Here the appropriate notion is a stratification. So here in this work we considered oriented piecewise linear manifolds. It doesn't matter much, but it's simpler in the piecewise linear framework. And we consider 2 manifolds and 3 manifolds for the surfaces and the cobordisms, and they can have a boundary. And then a stratification, in our sense, is some filtration by closed subspaces. So you start with the empty set, then you have x0, then x1, and so on, and all these subspaces are closed, like the skeleton of a CW complex. And then we also ask, so if we take this K skeleton and remove the K-1 skeleton, then we get different connected components, and the connected components of this are the strata. So generally the strata are often open, they're not necessarily closed. And we ask that the strata are oriented piecewise linear manifolds, and their boundary is contained in the boundary of X. And then we ask another condition, which is like a discrete, a piecewise linear counterpart of a certain condition in Lurie's work. We ask that it's locally conical, that it's oriented, and that it's framed. So I don't have time to fully explain it. So I've drawn pictures. So oriented means that all the codimension 1 strata, so planes in a 3 manifold, have a normal vector. Here also. And the codimension 2 strata, so lines in the 3 manifolds or points in the 2 manifold, they have an orientation. And locally conical means that if you have, it means essentially that the stratification does not change along a stratum. Like if you have a line here, and you have here 4 different two strata that go in, then, and you go along the line, then nothing is supposed to change. So you cannot have like one of the strata melting into the line. And the same here. Here you have a stratified sphere, like you have a small neighborhood of this codimension 3 stratum, the dot here in the middle, and in the small neighborhood it's always made up out of line segments that extend from this to the boundary of the ball, and then plane segments like here. And framed just means that you cannot have like a circle codimension 2 stratum with like different planes that twist around it. So like a Möbius strip with a line in the middle would not be allowed. That's what a framed means. Okay, but these are kind of reasonable assumptions, and in most of the work on the defects, they're always met, because otherwise you don't know how to handle the data. So this is the kind of thing we allow inside of the manifold. And now, to have defects, you need to assign to the strata appropriate defect data. And in the general situation, this would be some higher categorical structures. In this situation, it is also higher categorical structures, but you can describe them in a pedestrian way. Yes?
Sorry, I just have a very basic question on the previous slide.
Mm-hmm.
In that picture with the 4 surfaces meeting at a line junction,
Yeah.
is the 2 stratum the line itself? Or?
No, so the 2 stratum, one has to distinguish codimension 2 and dimension 2. So the dimension 2 strata are these planes. And the codimension 2 stratum in this situation would be a 1 stratum, because it's in 3 dimension, would be the line.
I guess I'm just asking about, you have this xk minus xk minus 1. So I'm supposed to take these 2 two-dimensional surfaces and subtract.
Here, for the line, the line is a one stratum. So here I've not drawn a vertex on the line, but if I had a vertex on the line, I would be supposed to remove this because it's dimension 0, and then I would get 2 bits of line. So from the lines, I have to remove the dots. From the planes, I have to remove the lines and the dots, and so on. So in this picture here, this would be a codimension. Let me show it like this. So here you would have a 2 stratum. That's one of these plane segments. The 1 strata would be the lines, but the vertex would not be included, and the 0 stratum is the vertex.
Sure. Yeah. I guess I'm just asking, when you take xk minus 1,
Yeah.
you're basically subtracting the line, right? From these surfaces.
Yes.
So is the line part of the graph, or?
The line is not part of the boundary. This is a different notion. So with boundary, the stratification can come up to the boundary of the manifold, and there it needs to be transversal. So we would not call this a boundary. We would just, this is part of the stratum. And the boundary would be, if the manifold ends at the bottom, would be these blue lines here. Sorry, I was not so clear about this.
Maybe there is a small comment. So these X's, these are not strata. These are unions of strata of lower and lower dimensions, right?
The skeleton, yes.
Yeah, exactly.
Yes. So these are the skeleton, like the skeleton of a CW complex. And then in a CW complex, if you remove the K-1 skeleton from the K skeleton, you're left with like all these open disks. And here they're not necessarily open disk, but it's a similar picture.
Sorry, I guess there are different notions of the framing, but you are assuming that the normal bundles are all trivial then?
Yes, so the framing plays only a role for us for the circles. And there we need, this is this dot here, we need to exclude the case that like these bundles twist around it. So yes.
So it's a trivialization.
Yeah, it's a trivialization. And I think one can see later where we need it. Okay. So now we need to assign to the strata different defect data. And the codimension 0 strata, they should be labeled as before. So for Dijkgraaf-Witten theory, we take finite groups. And here I should say what I'm considering is not the most general data. Even for the Dijkgraaf-Witten case, I could have finite groups plus co-cycles, but we do not have the co-cycle data here because it would make everything too complicated. So we just take finite groups. And for a codimension 1 stratum, we take a finite set with a group action. So here, here's the codimension 1 stratum, that's this plane. They have one group on the left, the group G, and one on the right, always with respect to this normal. And then we take a set M, a finite set, on which the group G acts on the left and H acts on the right. Okay. Out of this data, we can build an action groupoid. So what is an action groupoid? That's usually denoted like this. An action groupoid is a groupoid that is built from a group action on a set. So the object of the action groupoid are just elements of the set. And the morphisms are group elements. And if we start here at an element M, then the group element sends it to the image under the group action. So this is a general construction, and what we do with the codimension 2 strata is we assign representations of action groupoids, and that's just a functor from the action groupoid into the category of vector spaces. So here we have this picture here. We have 3 different planes, they're all labeled by sets. In between we have the codimension 0 strata, they're labeled with groups, and this line here gets a representation of the action groupoid. So a functor from this action groupoid to the category of vector spaces. And the action groupoid just collects all the different sets that are at planes incident to the line, so M, N, and P, and it collects all the groups that are incident here. And this is the data. And for a codimension 3 stratum, so this exists only in a 3-dimensional manifold, so in other words, we're talking about a vertex in a 3-dimensional manifold. We assign an intertwiner of action groupoid representations. So here we have the vertex, and we can have various planes here and lines incident at the vertex. And we collect all the planes that are incident at the vertex, we collect all the groups that are in the different regions here, and then we collect all the representations here. And the representations maybe do not depend on all the data of all the planes that it is incident here. So we have a projection functor that just projects on the planes that are incident to the line. And then we assign to this a natural transformation between certain factors. So that's an intertwiner of action groupoid representations. So this is the simplest possible data one can take. And the question is, how do we know it's correct? Essentially, we know from Dijkgraaf-Witten TQFT that it's correct. Or equivalently from the Levin-Venn models and quantum double models with defects. So in general, it would be a spherical fusion category, a bimodule category, a bimodule functor, and a bimodule natural transformation. And in this setting, where the spherical fusion categories are just spherical vector spaces graded by finite groups, this is like a subset of the data you can consider. Okay, so that's the data. And then we can define a defect cobordism category, where the objects are stratified closed surfaces plus some defect data assigned to the strata. And the morphisms are equivalence classes of stratified cobordisms, also with defect data. And the equivalence classes for the cobordisms is similar to the case without the strata, but everything needs to be compatible with the strata. So if I glue the boundary to a manifold, then the stratification must match and the data must match. And the tensor product, as before, is the disjoint union. Okay, so this is a defect cobordism category, and what we want to do now is to construct a symmetric monoidal functor from this defect cobordism category into the category of vector spaces. And one can do this, of course, with choices. Yes?
So, if I understand, in the codimensional one, you take any finite set of points that are connected by the group action.
So for the codimension one, I take a finite set with an action of the group, of the two groups that are assigned to the. Here, so here we have a plane that's codimension one, and then we have two groups that are adjacent to it, and then we take any finite set on which this group acts.
There would be many such sets.
There could be many sets, but this is data. This is something that we assign to the defects.
Some extra choice that you...
Yes, it's a choice. And also in this is why we say here, in the cobordism category, the defect data is part of the cobordism category. I mean, if you're doing Dijkgraaf-Witten TQFT without defects for a choice of a finite group, you are free to decide, is this like part of my cobordism category, this choice of the group, or is it just some external choice I'm making? But here you can have different groups, so you need to say in the cobordism category already which group belongs to which of the strata. And in the non-defect case, you just have a single stratum of dimension 3, and then it's kind of irrelevant to label it with a group. But here you need them.
So in which states do you expect to recover just regular Dijkgraaf-Witten theory?
I'll explain at the end of my talk.
When you don't have any defect.
We recover it.
Okay.
I'll explain at the end of my talk. Okay, so the goal is now to construct a symmetric monoidal functor from this defect cobordism category into the category of vector spaces, but not to do so by using a higher category diagrammatic calculus or triangulations and so on, but just the data of the stratification. And essentially we have three level here. So on one hand we have like a combinatorics of the stratification that tells you like which strata are incident to what other strata. And this we encode in a graded graph. And this graded graph defines for us a category. Then we have the topology of the strata. The strata are not just required to be disks like you would have in a CW complex. This would make everything too complicated. So the strata can be more general than disks. In general have a topology. They have a fundamental groupoid that is non-trivial. And then we have the algebraic data, so the defect data. And we organize this topological data and the defect data into functors from this category given by the graded graph. So that's the general strategy. So what is this graded graph? So graded means just that the vertices of this graph get a number, the codimension of the associated strata. So the vertices correspond to strata, and the number is their codimension, and then the edges describe which strata are locally incident to other strata. So I'll show this in an example. So here we have a stratification of a surface. We have two codimension 0 strata, the left one and the right one. Then we have one codimension 2 stratum, that's the edge here, and we have one codimension 1 stratum, that's the edge here, and one codimension 2 stratum, that's the vertex. And here we see that this edge is incident to the left one and to the right one. So we have here a dot for the edge, and we have one arrow here and one here. But the vertex is incident to the edge twice. So we have two arrows from the edge to the vertex. And in this graph, we only include the incidence where the codimension is lowered by 1 degree. So we include from the vertex to the edge and from the edge to the surface. Okay. And the topological data of the stratification defines a functor from the category that is generated by this graph into the category of groupoids. So what we can do is we can consider the strata, and we are cutting the k-skeleton along the k-1 skeleton. So this leaves us, we are in the piecewise linear framework, so everything is a simplicial complex. So we cut the k-skeleton along the k-1 skeleton, and we are left with certain pieces. And these are the spaces that we assign to the associated vertex here. So here we have a vertex, and we assign to it this space that corresponds to the stratum. And then we assign the fundamental groupoid of this space. And if we have a stratum that is incident at another stratum, like here, for example, the vertex is incident at the edge, we get a functor between the fundamental groupoids. And this is simply the map that kind of sends the lower dimensional stratum to the boundary of the higher dimensional one. And in this picture here, the space assigned to the vertex would just be a one-point space. So that's a dot here. The space assigned to the edge would be an interval, but it's a closed interval because we're not removing the dot now, not excluding it, but we're just cutting the circle at one stage. So it's a closed interval. And what we get here is the embedding of the point to the endpoints of the interval, 0 and 1. And here for the left and for the right, what we get as associated spaces is just the closure of them. That's not the case with the edge, because in the edge, if I take the closure, I get S1, here I get the interval. And then we get like an embedding of the, not an embedding, but a continuous map that sends the interval here. So that's what would happen. And then the defect data defines us another functor from this graph to the groupoid, into the category of groupoids. And what we do is we assign to each stratum an action groupoid, where we just collect all the sets assigned to the codimension 1 strata, and we collect all the groups assigned to the codimension 0 strata incident at the stratum. Okay, and how does this work in practice? Okay, so if we are somewhere inside here in this stratum, then there are no codimension 1 things, so there is no set with a group action, there's just a group. So here we get the group viewed as a groupoid with a single object, for the left and for the right. So at the edge is assigned some set with a group action. So for the edge here, we get just the action groupoid associated to the set with the action of the group on the left and on the right. The vertex now has two incidences of the edge, one here and one here. So I get two copies of the action of the set M that is assigned to the edge, and I get the group here at the left and at the right. So these are the groupoids that are assigned to the strata, and we have like every arrow here gives us a canonical projection functor. So here I project on one of the two copies of M, here I project on the other, and then here I just project to the group viewed as a groupoid with a single object. Okay, so this is just a rough picture.
Oh, I'm sorry.
Yeah.
That bottom right diagram, could you say again what the arrows are just projections? Is that what you think?
Yes. So here I have M times M over GL times GR. And then here I have a projection that just on the objects projects on the first copy or on the second copy, and on the morphism it does nothing. So these groups act still the same. And this you can see because here these two copies of M belong to the first end and the other end of the edge. And that's what is projected. But here the edge as well as the vertex has the two groups acting on the left and the right.
Right, and then the next level?
The next level sends all the elements of the set to the single element here in the one-point set and projects out one of the groups.
I see. Okay.
This was maybe a bit fast. But it's a very canonical construction, and it's somehow built in this formula already, because here I'm saying I'm collecting all the incident sets and all the incident groups. And if I have a vertex, there are potentially more sets and more group incident to this than at an edge and so on. So you get canonical projection functors. Okay.
One question maybe. Yeah. So what kind of stratifications do you allow? For example, if I have just one rogue line or one rogue point?
No, this is not allowed. I forgot to say this, but this is a good point. So we always ask that every vertex is incident at least one edge, and every edge is incident at least one plane, and every plane is incident at least one three-dimensional region. The reason is if we do not allow this, we need to impose all kinds of framings, and also this makes it a lot more complicated. I think also in other formalisms. Sorry, I should have said this. Yes, and that's also the reason why we here only consider the arrows that go to the next level, because I know if I go level by level, I will arrive at the top eventually. Yeah?
It's a bit abstract to me. If I have two vertices on the same circle, I can fuse them, I suppose. And that will give us data, and that data belongs to the logical or to the defect.
So for the, how should I say, we have different layer of data. So the data I'm looking at this slide is only the data that comes from the codimension 0 and the codimension 1. But I'm not talking about the functors of the action groupoids and the representations of the action groupoids and the natural transformations between them yet. And your question is about the data that is not yet present on the slide. This would be the composition of natural transformations, but the natural transformations are not there yet.
So these, what you call logical data, here it's just like information about incidents of some configuration of, your stratification that you fix, right?
The stratification is always fixed, because like every defect cobordism comes with a fixed stratification.
So how about, but then there's maybe another level of topology where you could maybe try to deform this stratification into something with the same type of incidence, right? But you're not considering that.
We are not allowing them to deform at the moment, but you will see from what we compute that in some cases you can easily deform them. But we are not making a statement on deforming them. For us, this is really fixed part of the manifold, yes. But you will see later that you have the possibility to deform them. But it's a question we are not addressing. It depends what you mean by dynamical, but this is really, for us, it's input data. It comes with the defect, it comes with the stratified manifold, and it's fixed, it's in the category already. But that doesn't mean you cannot do dynamical things with it, but we are not treating it as dynamical as dynamical at the beginning.
Maybe a related question. Since it's a choice, and I guess you chose it so that it reproduces the known defects of Dijkgraaf-Witten theory, if you have chosen defect data in a different way, but such that the stratified TQFT still reduces to Dijkgraaf-Witten theory when you only consider unstratified.
So when I say it reduces to Dijkgraaf-Witten TQFT, what I mean is that you can have certain defects that are labeled with what one calls transparent data. I'll come to that at the end of my talk. And if I choose a different data at the beginning, as long as the transparent data is still contained in my data set, then it will give exactly the same thing. So it's essentially, you can switch the defects off by putting appropriate data on it. And now I could make it a lot bigger. I could say I consider general spherical fusion categories, and then I restrict attention to the case where they're given by groups and completely general data. But for switching off the defects, I would still have to take the trivial data. I'll explain this at the end.
Oh, sorry, I should have asked this earlier, but when you were looking at four-dimension 3 data, you had this natural transformation of functors, right?
Yeah.
Now, the functors are functors from, say, G sets for a fixed G, right?
Yes.
So when you take tensor product of these functors, these are you take products of groups and products of G sets.
Yes, this was in this projection functor. So basically what I can do, if I have several lines that are meeting with like planes coming out of them, I just accumulate all the planes around the vertex, and then I have projection functors that for each line project only on the relevant planes.
I just wanted to understand the tensor product of the representation.
So the tensor product is like the pointwise tensor product of the functors, but the functors are always composed with the projection. I'll come back to this. Okay, so in this way one can associate to each stratified manifold a gauge groupoid. And this gauge groupoid is defined only by the defect data of codimension 0 and 1. And this is done in a categorical construction with an end. And this construction ensures that for each stratum I get a groupoid, and I get a projection functor from the bigger groupoid that is assigned to the stratified manifold into the groupoid of the stratum. And that's the functor I use. And then we also have, for the boundary, we get another groupoid, and we get a functor that goes from the groupoid for the manifold X to the groupoid for the boundary. I'll explain this later in an example also. So this is simply something that is a consequence of this definition, but it's not, it takes a lot of time to derive. And one can look at this in a more concrete way. How does this groupoid that we assign to the stratified manifold X, how does it look like? So the objects of this groupoid should be gauge fields. What is a gauge field here? So a gauge field is an assignment that assigns to each codimension 0 stratum a functor from its fundamental groupoid into the group with a single object. Plus it's a map that assigns to each codimension 1 stratum a map from the associated space into the set that belongs to the stratum. And this has to satisfy a compatibility condition, and this compatibility condition here is related to parallel transport. So here I have this blue codimension 1 stratum S, and I have a path on this codimension 1 stratum. And above and below I have two codimension 0 strata, T prime and T. Now, if I take a path on this stratum S, we have endpoints, and these endpoints by this map here are assigned certain elements of the set. On the other hand, this path can be embedded into the space for this stratum here and the space for this stratum here. and there it gets assigned a group element. So this part gets a group element of the group associated here and a group element associated to the group here. And what one then does is say, one imposes that the value of this map here and here is related by the action of this group elements. So this is like a parallel transport condition. And the morphisms are gauge transformations. They are assignments of each codimension 0 stratum a map. So we have points here, and every point gets assigned a value in the corresponding, an element of the corresponding group. And they act on the gauge fields for the codimension 0 strata in the usual way. So we have left multiplication and right multiplication here at the endpoints of paths. And on the data in the set that is on this blue stratum here, it acts pointwise. So if we pick a point here, then we have a group element assigned to it above and a group element assigned to it below. And these two act on the map, on the set. So in principle, you could leave out this definition here and just define it concretely via this definition. And well, then you would have to make more checks, and you would have to construct this. But you could also just take this definition, then derive this, and then kind of spend all the work working out what it's concretely. So this is a groupoid associated to a stratified manifold. And that comes from the codimension 1 defect data and the codimension 0. And what we could show is that this assignment that it assigns to a stratified manifold, this groupoid here, that this defines a symmetric monoidal functor from a three-dimensional defect cobordism category into a category of fibrant spans of groupoids. What this means is if I have a cobordism like here, so I have a 2-manifold sigma 0 as the 2-manifold sigma 1 and a 3-manifold x, then I get a groupoid assigned to x and projections on the groupoids assigned to sigma 0 and to sigma 1 here. And fibrant, so this is a span, and fibrant just means that the induced map into the product is a fibration. In physics language, this would mean if I do a simultaneous gauge transformation on the surface sigma 1 and on the surface sigma 0, there would always be a gauge transformation on x that just restricts to those two, here and here. And that's important for it to be well defined. Okay, so this is already quite close to a TQFT, but what we have here is not the category of vector spaces. So what we need to do now is to go from here to the vector spaces.
Sorry, if you don't have this fibrant condition, you have something like an anomaly?
Here we have just proof that we have it, so we always have it, and we had to show it.
Okay.
It would be something, yeah, I think you would call it an anomaly, but it could not happen with this data.
Well, if you had a cocycle.
With the cocycle, we don't know if it can happen, but it's like something where you have a gauge transformation on the boundary and no gauge transformation in the bulk that can kind of fill it in and restrict to those. Yeah. Okay. So now we have to take into account also the defect data on the defect lines and points. And this codimension 2, at least 2 defect data, this defines a diagram for a symmetric monoidal category, namely the category of functors from the gauge groupoid to the vector spaces and natural transformations between them. So these defects are the red ones. They sit inside of this manifold X and the surfaces, so there can be some dots on the surfaces where it comes up to the boundary. And they define a diagram for this category. So here we have as object functors from the groupoid to the vector spaces and as morphisms, natural transformations between them. Okay. And what one can do now is one can combine these defect data for the surfaces, basically these dots. Each of these dots carries a representation of an action groupoid, not necessarily the same action groupoid, but from the action groupoid of the surface, the gauge groupoid of the surface, we can project down to the action groupoid for each dot. And then we can all combine them by just tensoring them, and in that way we get a functor from the groupoid into the category of vector spaces. And we do the same here. We just collect all the functors that are assigned already to the endpoints, to these dots here. We collect them, we tensor the vector spaces, and we get a functor here. And then in the middle, we have the gauge groupoid of these three-dimensional manifolds. So it comes with these projection functors to the gauge groupoids of the boundary. And to this here, we assign a natural transformation between the functor that is assigned to this surface and the functor here, always composed with the projection. And this natural transformation is basically given by collecting all the natural transformations that sit at these vertices inside of the manifold X. And what one can show is that this evaluation procedure defines a symmetric monoidal functor into another category, namely from the cobordism category with defects into a category of fibrant spans of representations of groupoids. So here we see the fibrant spans of the groupoids, and then here we have this functor that goes into vector spaces, and here we have the natural transformations. And they form another symmetric monoidal category. And there's another symmetric monoidal functor from this category here, that is the target here, to the category of vector spaces. That basically takes the limit of these functors here, and these natural transformations induce a linear map between the limits. And the claim is, if we now compose the two, we get a defect TQFT. And what I should say is this functor L is not completely new. There were earlier works by Trova and also by Schweigert and Wolke that constructed such a functor in a slightly different setting. So the idea was already there, we just had to adapt it. Okay, so in this way we can construct a defect TQFT, and with this defect TQFT we can also compute. So now I treat the old example. So we have again this defect surface with the left and the right stratum. Then we have an edge here and a vertex on the edge.
So can you go back? What is this limit that you're taking? This is another regular.
So this is this functor L. It's a limit of a functor. It's a categorical limit of a functor. The usual notion of a limit of a functor. So that's not the problem. We have a functor, and because the category of vector spaces is complete and co-complete, we can take a limit.
So you're talking about directed limits, basically.
It's not directed limits, because here we have an action groupoid, but it's similar to directed limit. Yeah. It's basically something like invariance, taking invariance or co-invariance, which doesn't matter. And you will see it concretely how it takes invariance. Moment. Okay, so now one wants to compute something concrete. So we take this two-dimensional surface again. So here we have finite groups, GL and GR. Here on the edge we have a finite set on which the group GL and GR act. And now one wants to compute the vector space assigned to this defect surface, which should be something like a generalized ground state of a quantum double model with a domain wall, and here a domain wall junction. Okay, how does it work? So first, we have freedom in computing the gauge groupoid. The gauge groupoid is only of interest up to equivalence. So what we can do is we can reduce the gauge groupoid by just considering everything with respect to this vertex here. And if we do that, then we see that the gauge field becomes a triple of group homomorphisms from the fundamental group of the left surface or the right surface with respect to the space point into the group GL or GR. So this is very sensible, because this is what one would have in Dijkgraaf-Witten without defects, only we have it twice because this vertex here belongs to left and to right. And the remaining datum is the element of this set assigned to the edge here. So this is what the gauge field is. And the gauge transformation is even simpler. It just consists of two group elements, one on the left and one on the right. It acts on the group homomorphisms by conjugation, like it should, and it acts on this element of the set by the left and the right action. Okay. Now the defect vertex, here, it should get a representation of an action groupoid. So here we have two edge ends that are incident at the vertex. So we take two copies of M, and then we have the group on the left and on the right that is incident at the vertex. And this gives us a representation, so a functor from this to the category of vector spaces. And the vector space assigned to the surface is then the limit of a certain functor. So what I do first is I take the groupoid for the surface, so this groupoid here, I project to the groupoid of the vertex, and then I apply the functor f. And how does it work concretely? This limit, so it's basically a sum over gauge equivalence classes of these group homomorphisms and the element of the set. Then we plug in the element m on one side in one argument of the functor, and in the other argument of the functor, we plug in its image that we get if we go once around the edge. So this makes sense. So if the element m sits above, and I want to go below the vertex, I need to go along the edge once, and this gives me group elements on the left and on the right, and we say the two ends are related by that. So that's a concrete formula for this vector space, and one can also work it out for specific choices. So what I can do first is I can do something like a transparent vertex. So what is a transparent vertex? It's a vertex that is basically not there. And before, we had assigned here the element m, and here below the vertex the element m prime. This is m prime. And now we put a transparent vertex, so if the vertex is not there, the element m and the element m prime, here, they must agree. So what we put as a functor here, as a representation, is just a delta function, so m and m prime must agree, otherwise the functor just assigns 0, and then we take a copy of C. And if we want to put this transparent vertex, then we see that the vector space becomes just a free vector space spanned by equivalence classes of these triples here. So we have the gauge field, and there's one additional condition. Because we ask that this element m and m prime here must agree, here we do not admit all the different elements of the set, but we only admit the fixed points. So the elements m, that if I go once around the edge, I get the same element m. So here we get a fixed point. And then we can also say we make not just the vertex transparent, we make the edge also transparent. What does this mean? Well, if there's nothing there on the edge, then the two groups here and here must agree. So we have G left is equal to G right. And this is also what lives here at the non-existing edge. So the set M is also the same group. So we put them all equal. And then this left and right action on M is just the left and right multiplication. And in this setting, we can again compute what we get for this vector space, and then we get the vector space from Dijkgraaf-Witten without defects. So basically, we could switch off the defect and switch them on. So the weakest possible defect on this edge is just the group acting on itself from the left and the right, and the strongest possible defect we could put here would be like a one-point set or some other set with a trivial group action. And in this way, we can recover the Dijkgraaf-Witten TQFT and without the defects. But we can also consider such surfaces, and without choosing any triangulations or any additional stuff on top of the stratification, we can just compute what is this vector space for here.
So just one question.
Yeah.
So in Witten theory, you have these for the generators, you have this expectation in terms of flat connections, right?
Yeah.
So if this is not, if you have more than the transparent.
If I have not the transparent, then it's like the flood connections are kind of interrupted. You have a flood connection on the left and a flood connection on the right, but on the edge it makes no... Yeah, they're for different groups.
So how do you make sense of that?
Well, you could take the product of the two groups and you could quotient out something of the product. And this is precisely the way how you get a set with a group action on the left and on the right if the group action is transitive. So if this set here, the set M with the group action has a transitive group action, it's just a certain quotient by taking cosets of the product group with respect to some subgroup of the product. And the subgroup can be different, like you could say, okay, say the group on the right acts trivial and the group on the left not, then you would basically switch off the entire thing here.
And what is the role of these arbitrary space where the groups act? How do you?
Well, this is a choice you can make. Like you can, it's like you choose the set. This is part of the data, and you can make different choices. So if you choose it to be transparent, like in this case, then you simply get the Dijkgraaf-Witten without defects. You could also choose this set, for example, as a one-point set. Then you're just cutting it apart. Then these two don't talk to each other anymore. What you could also do is you can take the group, you could say we take the group G left, also for M, and we take G right, trivial, and then you would get something like a boundary that is not a gluing boundary. So it's a choice. It's different choices you can make. I know. Okay. So maybe one last example that shows how it works for three manifolds. We can consider a three manifold that is made by gluing handle bodies. So H1 and H2 are two handle bodies that are glued along the common boundary of genus G. Then we do the same thing. Each handle body gets a finite group. The surface gets a finite set with an action of the two groups. We choose a base point to make the computation simple. And then a gauge field is again given by two group homomorphisms from the fundamental groups now of the handle bodies into the relevant group. And now we have to pick for M a fixed point with respect to the action of the fundamental group of the defect surface. Basically what we have here, we have the surface where the two handle bodies overlap. We can go from this fundamental group into this product. Then we get the representations. These group homomorphisms, row 1 and row 2, then we go to G1 times G2, and then we can act on the set M. And then a gauge transformation is again a pair of groups. And in this case, you can compute what is the state sum. So this is a linear map from C to C, because there's no boundary. So it's just a complex number. It's like an invariant of stratified manifolds. And what you get is your sum over all conjugacy classes of group homomorphisms. So these are conjugacy classes, these brackets here. So you sum over conjugacy classes of group homomorphisms for these handle bodies. And then for each pair of such conjugacy classes, you're considering the number of fixed point with respect to the action of the fundamental group of the surface. So this is a sensible quantity to associate to this. And again, if we pick a transparent surface, so the two groups are the same, and they're also the same as the set, then we recover Dijkgraaf-Witten TQFT, so we get just the number of group homomorphisms from the fundamental group into the group G up to conjugation. So that shows that what we are doing makes sense, because otherwise, if we wouldn't get back Dijkgraaf-Witten, we would have a problem here. Okay. I have 40 seconds for some open questions. So what I'm really interested in is, like, if we have the two-dimensional part of this should give Dijkgraaf-Witten with defects, should give us a way of computing some kind of generalized ground state of Levin-Venn models or quantum double models in the presence of defects. Normally a ground state is not ground state because it comes from a TQFT, but ground state is ground state of some Hamiltonian. So I would find it really interesting to see how this could be described in terms of a Hamiltonian, and also how to generalize this Hamiltonian. Maybe the Hamiltonian, once one has it, for such a generalized ground state with defects, maybe one can also generalize it beyond Dijkgraaf-Witten to some spherical fusion categories. And maybe one could also use this to understand the moving of excitations through domain walls, because it's a fairly simple description. Yeah, other questions that I'm interested in is to understand our formalism better in terms of exit paths and the homotopy category of exit paths. So this was mentioned in Luca's talk. This is a fairly abstract framework developed by Lurie to describe stratifications. Our stratifications are much simpler, but one should make at some point a connection. Yeah. One should also include co-cycle data, and at some point one would like to understand how this is related to a diagrammatic description. So this is an ongoing PhD project. And of course, the big goal would be at some point to generalize this to a zero TQFT with defects and really give a nice formulation that is simple to compute and does not need the triangulations. Okay, thank you for your attention.
Thank you for the very nice talk. Are there any questions?
I didn't quite, could you explain again what you meant by description in terms of Hamiltonian?
Okay, so what I mean is there's like in the condensed matter physics and topological quantum computing literature, there's like what you do is you take a triangulation of the surface or maybe some other cell decomposition, then you put group elements on the edges of this triangulation, and then you have for every vertex, you have some vertex. So this is like some endomorphism of a big Hilbert space, and then for every plaquette, you have some operator BP that goes also from this. And then you make the Hamiltonian, that's something like the sum over all vertices and the sum over all plaquettes. Now I think it's 1 minus AV plus the sum over all plaquettes, 1 minus BP. And what this here implements is basically the vertex, this corresponds to the gauge transformations. And the BP corresponds to flatness of connections. And now one would like to think, at least if one puts maybe some domain wall into it, if one puts some domain wall into it, let's maybe put it like that, then one would say maybe this here is no longer labeled with G, but this is labeled with some element M, and this is labeled with some element M prime, and then this kind of flatness condition here should be modified. And I have some idea how to do this, then this would be something like to ask some delta function, delta M prime, what does this letter, it's G, delta M prime of G acts on M. Like some weakening. And similarly for the gauge transformation, we would say if we put a vertex and this edge here goes through a domain wall, we would put maybe the action on the set and not the left multiplication. And in this way one should be able to generalize it, and then one should be able to maybe construct a Hamiltonian in along these lines, and then really say, okay, in the presence of domain walls, the ground state of this Hamiltonian, the lowest energy state, is precisely what comes out from this formalism.
The 2D.
Yeah, yes. Yes, that's what I'm thinking. But I don't know what a Hamiltonian is or what it should be. I know roughly how to generalize this and this, but I don't know what is the correct Hamiltonian. I mean, physics correct Hamiltonian. I think there's more considerations than just mathematics.
So maybe a quick question, yes?
Yes, so if we consider the topological lines of the divergent theory, so let's say some modular tensor category, a particular class of defects would be the ones labeled by modules over that modular tensor category. So the labeling that you have in yours is
module categories over the fusion category or modular tensor. Yes, yeah, I mean what we have is like fusion categories is something like vec G, and then we have a bimodule category like a vec G, vec H, bimodule category, And this bimodule category is just vec M, where M is the set with the group actions. And
so these are the domain walls that you
yeah, yes. And then the lines are just representations of action groupoids, but the lines are really bimodule functors. And the vertices bimodule natural transformations. And one other thing we could recover here would also be like the Drinfeld double of the group and so on.
Okay, last very quick question.
Sorry, I'm hoping I can ask more or less the same question I asked earlier one more time. So, ordinarily in physics, when one is doing TQFT, the data that labels the defects is an output. But in your approach, it seems like it's an input. So I guess what I'm wondering is there something that like forced you to choose your defect cobordism category in the way you did once you declared that you're dealing with Dijkgraaf-Witten theory in the bulk, or?
Well, I mean, it depends what you mean by forced. So if I have like Dijkgraaf-Witten theory, if I start from the viewpoint, the Dijkgraaf-Witten TQFT should be associated to the codimension 0 strata, then it's fixed that I have to have two groups, G and H, and then if I put a domain wall, then I need to put a set with a group action. I mean, I can describe this in a slightly different or more general way. I can say instead of a set with a group action, I can put this. And here I have a little bit of freedom. I can choose another thing like a co-chain or a co-cycle and so on that we have left out for simplicity. But that this is some data you put in is kind of also in the physics. Like if I have a domain wall between two different phases, I mean, there could be several possible domain walls. Say you have two semiconductors and you have a boundary, and maybe this is a completely different material that you decide to put in. You could put a metal or you could put a plastic and so on. So they're not dynamic in that sense.
Okay, so maybe let's postpone other questions and don't escape yet because we'll take the photo now, and let's thank Katrina.